All right. First of all, thanks for the hoodie. I have to wear it. Yeah, welcome to this session, What the CRaC, Coordinated Restore at Checkpoint on the Java virtual machine. First of all, who knows what checkpoint restore is? No? Okay, yeah, some people know. It's pretty simple. When you work with your laptop and in the evening you close the lid, you just close it, right? No problem. Next morning you open it and it starts where you left it. That's checkpoint restore. That's exactly the same thing, just on an operating system level. So the operating system detects closing the lid, it saves the whole state of the operating system, including all apps, to the disk. When you reopen, it just restores everything back to memory. That's checkpoint restore. Sounds easy, but we will see it comes with some problems sometimes. First of all, my name is Gerrit Grunwald. I'm working for Azure. Yeah, I even have a shirt that says I'm working for Azure. Yeah, here you see, so I have to do that, right, in the camera. I'm working for Azure as a senior developer advocate. I'm also a JAG leader. I lead a Java user group in Münster, Java champion, and all this other stuff. I'm working with computers since 1982, so I'm not that young anymore. But that doesn't really matter here. So Java is great, right? I mean, we have a vibrant community, as we can see. People show up even if there are other people close to us trying to hit this meeting. No chance. We have thousands of free open source software projects. And the real star of the whole thing is the Java virtual machine. I mean, I think we are all Java developers, more or less. I'm not really, the language I don't care, but the JVM is the important part. The question is, how does it work? Probably most of you know better than me how it works, but nevertheless, I will give you a very easy, simple introduction because sometimes it just helps, and for this session it probably helps to understand. So we start with the source code, which is just a Java file, and then we put that into the Java C compiler, and the Java C compiler spits out a class file, which is cross-platform. This one contains bytecode. And then we take this class file and use a class loader. And the class loader alone is a topic you can talk about for hours. But in this case, it's just a class loader. And the class loader takes this class file with the bytecode and loads it into JVM memory, right? And once it is in JVM memory, which is again complex, this is very simplified. From the JVM memory, it gets into the so-called execution engine, which is a part of the JVM. The JVM has three parts. It's the class loading part, the memory part, and then the execution engine. And in the execution engine, we have these 5 pieces. Where we have the interpreter, the C1 compiler, C2 profiler, and garbage collector. And the compilers, I mentioned here client and server compiler, and I see some gray hair in the audience. So that means I assume you guys know what client and server compiler means. The younger ones probably don't know that. The C1 compiler before JDK, I think it was JDK 7. You have to choose the compiler you would like to use in the JVM. And if you run it on the desktop, you usually use the C1, the client compiler, otherwise the server compiler. And the difference I will explain in a second. So since JDK 7, it was possible to use tiered compilation. That was a flag. And then from JDK 8 on, that was the default. So now everything is, both of these compilers are part of the JVM always. And they work together in this so-called tiered compilation. But we only look at these 3 parts because the garbage collector, you can talk for hours, and the profiler is also not that interesting here. What happens is the interpreter takes the bytecode from our class file, interprets it line by line, and converts it into the instruction set of the CPU. And the JVM is profiling it, it's looking at that, what's happening, it's counting methods. That's how often is the method called. So something that many people don't know, on the JVM, the smallest unit is the method. So that means if you put all your code in the main method, there won't be any compilation. It will run in interpreted mode only. So only if you use methods, then it will start counting the method calls, and then it will, after it reaches a specific threshold, it will take these methods and we'll put that into the C1 compiler. And the C1 compiler, as I mentioned, is the formerly known client compiler. And the reason for that is that it compiles code very quickly without really doing any big optimizations. And the reason for that is it's obvious because it was the client compiler. If you run your desktop application like IntelliJ, Eclipse or whatever, you don't want to wait for seconds just to have the compiler do the best optimizations ever. You just would like to have the application started. That's the main idea. So that's the reason why the C1 compiler is just fast, doesn't do a lot of optimizations. And then once again, the code is running, the already compiled code. And again, it's methods, right? And the JVM is again watching that and checking how often this already compiled code methods have been called. And then it takes this method after it reaches another threshold and puts that into the C2 compiler. The C2 compiler is more complex than the C1, and it's a beast. So it was already created by Sun back in the days, and it still gets some updates, but people are really careful because it's old code, it's complex code. You don't want to break it. But it's good. It creates very fast, optimized code. It takes a little bit longer because it's more complex, does a lot of optimizations. But once it passes that, the code is quite fast. This is what we usually define. This is the whole procedure. That's the JVM warmup or startup time that we see. And this is called tiered compilation. And that we have different levels. So that means you will find code. If it's not called often enough, it will never get compiled in the JVM because it's not needed. If it's fast enough to interpret it, then it will stay in level 0. We have 3 levels for C1, and this is the reason is you can do no profiling, and then you can do a little bit of profiling, like basic profiling, and you can do full profiling. And the reason for that is that, and we have level 4, which is C2. And the profiling here is needed because the C2 compiler gets the profile information from C1. So it can use this information already to further optimize the code. That's the idea, and that's the reason why we have that. And usually this is the ideal way, the standard way. So we have interpretation, level 3 means C1 with full profile, and then it goes into C2. But this is not always the case. So it's really, there are lots of different cases where code, for example, can't be compiled in C2 because the queue for C2 is already full, so it stays in C1, and then when the queue is empty, it goes to C2, and all these things. There's also code that get interpreted, and then the compiler, the JVM figures out, oh, it's not worth to compile the code, and it goes back to interpretation. It stays in interpretation. So it starts compiling and then goes back. So there are lots of different changes between these levels. And this is just the standard. And then that leads me to the execution cycle, which is more or less the same that I explained just in one image. So we start with interpretation, which is slow, finding hotspots, which is the name of the hotspot compiler. And then we go to C1, fast compile, low optimization, again profiling. Then it goes to C2, and then we have this thing here. And this is de-optimization. Who knows what de-optimization is? A few. Yeah, it's interesting because usually people don't talk about that, but it happens all the time. It can be a performance hit, and I have some slides about that. The optimization is, in principle, if we take this code, a simple method, we put in a value, and then depending on the value, it has this if-then clause here, or if-else. And it just checks if the value is larger than 9, then it will compute something. If not, the result will be 1, and then we return the math log 10 from this one, for example, plus 99, or from the result plus 99. So the flowchart looks similar to this. This is just a pretty simple example. And this is one optimization possibility, which is called branch analysis. So what the JVM is doing, it checks this running code. It's a method, so it checks this code. And then it figures out, you know what? All the time, the value was never greater than 9. That means it always calls this one, right? So it's always false, it's always 1, and then 1 plus 99 is 100, and the mathlog 10 from 100 is 2. That means this will be the code that will be created internally in the JVM. instead of having all this code that was in the method for the compute value thing, it just has another code which is common trap. And if this is not the case, then it just returns 2, because that is directly the result of this calculation, right? So this we optimize this code to that code. And if the value is never larger than 9, it will always return 2, and you can imagine that's really fast. And we did some measurements with this so-called, what's the name of it? It's I forgot the name. It's all these optimizations that can be done. It's speculative optimizations. So that means the compiler does really some speculating about, it looks like this code has never been called, so I just remove it. The compiler can be wrong, and then we have de-optimization. In this case, that means if the value suddenly is larger than 9, then it has to de-optimize, and that means this method will be called, and this whole block will be thrown away. The compiled code will just go away, and then again this code will be interpreted, C1 compiled, C2 compiled, so the whole method. You can imagine that once it was here, it's fast, suddenly this happens, it has to go back to interpretation, which is slow. That's the performance. That's de-optimization. On the other hand, you can imagine that if the behavior of the application changes, the compiler can react on the changes, because it can de-optimize and optimize for the new behavior of the application. And that's the big benefit of de-optimization. So it's good and bad at the same time. If we take a look at the JVM performance graph, then we see these 3 colors here, which is the yellow one is the interpretation, then the green one is C1, and the blue one is C2. And you see interpretation it's quite small. It's really quick. If methods will be called a lot, then they move through interpretation and then directly C1 and then C2. So it means this is interpretation, C1 compiler, C2 compiler. And then we see all these gaps here, right? So these are some frequent gaps on the right side, and this is garbage collector pauses. Even if the garbage collection pause is just 2 milliseconds, there is a performance hit for 2 milliseconds. It's something like stop the world, right? More or less. Even if it's tiny, you will see these gaps. Then we see these big gaps here. And this is the optimization. And you see here, for example, the compiler was already, the code was fast, and suddenly something happened, and then it drops to this point, and then again goes through interpretation C1 and then C2 again. So that's okay. We know this is the warm-up phase of your application in the JVM, and that's all great, but it takes time, right? It doesn't come for free. And if we take a look at the JVM startup, I have to clarify some words here because people mess that up these days more often. It's you probably heard about this in the microservice world, and people say, oh, the JVM sucks, it's so slow, and the JVM startup and all this bullshit. Why I mention that is the following. If you just use a JVM, you put in one class with one method and just system out println hello world, then tell me this is slow. You started, it's there. This takes some milliseconds. This is the JVM. The JVM is fast. What makes the startup slow is your code. This is the stuff that needs to be compiled and interpreted and all these things. This is your code which makes the JVM startup slow. It's not the JVM, it's your code, right? So that means if you have a large code, it takes longer. So don't blame the JVM. This is just how it works. And usually what we do is we define this whole process of JVM initialization plus the application startup. This is JVM startup. This is time to first response of your application. This is what we define as JVM startup. So when I say JVM startup, I mean this whole thing, including your application. It doesn't mean your application is optimized yet. It just means it's the first time it comes back to you, right? And then there's another thing which is called application warm-up. That's a different thing. Because let's say, for example, you have a high-speed trading application. And these applications needs to be warmed up. So that means you have to make sure that all the code is really optimized as good as possible, because really milliseconds count. That means you need more time. It's not enough just to wait for the first response. You really have to make sure that it's fast all the time with every call you do. And this could be hours. right? So we have customers, they started up the JVM at 4 a.m. to make it fast at 8 a.m. when the market opens. And this is not unusual. So in this trading business, they do that. So they start up the stuff sometimes at midnight just to make sure that at 8 a.m. when the market opens, it's fast. And yeah, you can imagine that it doesn't only take time, it costs money to run the infrastructure for that time. And they have to shut it down in the evening. When the market closes, there's no reason to keep it running. Why? There's nothing going on, right? Okay, so this is JVM warmup. That includes all of it. That means startup of the JVM, application startup, and then the warmup. Could be also filling up caches and all these kind of stuff. Okay, that's just to make that clear. So if people say the JVM sucks because it's slow, you know how to handle that, right? Okay, so if we take this to microservice environments, which are the thing these days, then that means at the first run of a microservice, we have to go through this loop to make it fast. The second run again, third run again, and that sucks. Because it's every time you have to go through this startup time, right? Which is, wouldn't it be great if we can do something like, first time you start it up, second time, you just go from here, full speed, and third time again. That would be perfect. That would be the perfect solution. Well, let's take a look at some solutions that are available today that can help with startup time of the JVM. So first thing is class data sharing. Who knows that? Some, right? It's not really well known. It's in the JVM since JDK 5 already, but it was enabled per default from JDK 12. That means if you're on 11, then you use it without knowing it because it's enabled, but you can fine tune it. So it works per default not as bad, but you can even make it faster. And what it does, you can think about it like if the class loader starts collecting all the classes from the class path, then it has to load it from different files and do all these things. And instead of doing that all the time, you do it once, and then you store this file representation in a specific format in one file. And you can imagine that the next time you load it, you just load one file, which is much faster than loading all the different files, right? Because you have to open it, load it, close it, and so on. And so you just load one file, and it's already optimized format, and then this is much faster. And it's shared on each JVM start. You can also share it on application level or JVM level, it depends. There's no optimization or hotspot detection. This is all class loading time, right? So this is not really something that helps us with all this compilation startup. Like I said, it only reduces the class loading time, but you can get up to 2 seconds faster startup time, which is a lot if you think about it. Because when we hear people from GraalVM, native image, they say, oh, you see, we can get down from 2 seconds to 50 milliseconds. Well, you can also save time here if you know how to do it. And if you would like to know how to do it, then you should check the blog post from Ionut Balozin. He has a blog. He has not only a blog post about it, he also has a session about it, which is really, he tells you how to get the most out of it, out of CDS. Okay, so and it happens here, just to make that clear. So before we get into JVM memory, so that's even before we get into interpretation and all these things. That's nice, but yeah, doesn't really help us with our problem. Then there's ahead of time compilation, which you all know probably, mainly GraalVM. And so I have to ask, is someone using GraalVM in some projects here? In production?
Not really.
Okay, because it's really rare, it's not really a lot of people use that. Well, we don't have to interpret bytecodes here, and there's no analysis of hotspots, no runtime compilation of code, and we have super fast startup time straight away, and GraalVM native image does exactly this, right? So that means problem solved, right? So we have our fast startup, that's perfect. Well, not so fast. AOT is by definition static, right? We already said there's no hotspot detection and all that. That means because it's static compilation is the same as if you compile C code. You do static analysis, you compile the code as it is, and that's it. So it's compiled before it is run, usually, right? If I just talk about AOT. And the compiler has no idea what's going on. It just sees the code. They are really smart static code analysis tools, but still, it has no idea what the code is really doing in the end. There's one thing that can help, which is called PGO, or Profile Guided Optimization. So that means you run the code once and create a profile, and then when you create the native image, you take that profile and apply it to this native image creation. This is not everywhere available, but if we take a look at the JVM performance graph, then usually, if you just have plain AOT compiled code, you get up to 60–70% of the JVM speed. And if you have PGO, which is only available in GraalVM Enterprise, which, by the way, they changed their license model. You hopefully know about that. So, because in January, they had this pretty nice idea to change from node-based or core-based to employee-based, which is great, right? So that means you have a company with 10,000 people. One is using Java, you pay for 10,000. That's what it means, which is just keep that in your head. And it also applies for GraalVM Enterprise. So that means you don't get this with GraalVM Community Edition. You can only get this. And before this session, because that's the first time I show that, I always said I don't have hard numbers here because I really didn't test. But I found some numbers, right? I found it. Beldon.com has a nice comparison between Spring Boot and Quarkus, native image and standard, which is cool because I found exactly what I need. Startup time, here you see the JVM version, and this is the native one, right? GraalVM native image. It's much faster, as I said. And there's no doubt about that. Artifact size, yep, it's smaller. 30 megs, 94 megs, 3180. Okay, I agree, that's fine. Heap size at startup, for Spring Boot native, there is no, because it's a native image. For the JVM, of course, and it's big. You see it's really huge, which is fine. Interesting is used heap max. It's okay, it's smaller, but still 529 compared to 782 is not really that big, right? The difference. And the reason is, yes, you have a native image. Yes, it's smaller. At deploy time, once your service is running and it drags in data, it will blow up the memory anyway, right? So this is really just the deployment size is smaller. Doesn't mean at runtime it's smaller. Because once you start working, it's the same code in the end. Once you start working with your maps and lists and all that, so you drag in data from it will get close to the original one. But the really interesting part is that this is requests per second. This is the JVM code. This is the native code, right? And you see, for Spring Boot, it's just 74% of the JVM speed. And for Quarkus, it's just 53%. And that's great, because that's exactly what we claim with the 60%, because they use GraalVM Community Edition. If you are fine with that, that's okay. But if you lose 50% of performance just by getting the benefit of a smaller deployment image, that's fine. But just keep that in mind, right? So it's nobody talks about that. It's slower. And you can test that. Just use your own code, run it in the JVM, create a native image and test it, and you will see it's slower. Yeah, right? So this is just something you have to keep in mind. I'm grateful that these guys did the test, because I didn't know exactly. So that means if we compare that, AOT versus JIT, then it means AOT has limited use of method inlining, because they only can do that when they compile it, where the JIT can do that all the time, even at runtime. No runtime bytecode generation. The JVM can do that all the time, of course. Reflection is possible. They have, I think it's called properties for each library. You need that in GraalVM to make it happen. But still, it's, if you have to convert from a JVM project to a native GraalVM image thing, this is often a problem, reflection. In the JIT or JVM, it's no problem at all. You can't really use speculative optimizations, because these are going on at runtime. And because this is compiled before it is run, so you don't have that. If you have PGO, you can do that, but like I said, GraalVM Enterprise Edition, not in the community thing. Overall, all performance will typically be lower. We saw that. This is true. On the other hand, one more thing, which is, I think, the most important one. If you have, we are Java developers. As soon as you create a native image, you step out of the Java world into the native world. That's fine for running, but have you debugged these things? It's not that easy. It can be tricky. There are tools, they do that and they're getting there. IntelliJ is also getting there slowly. But it's a totally different story because it's not Java code anymore that is running, and native code works differently than Java code. Even objects, even specific variables are not, it's not the same. I had one guy who approached me and said, we have a Java project and we have more than 90% test coverage and all tests are green. When we create the native image and run it, it fails. What should we do? No idea. It's really hard to debug that, right? So this is the problem that I see. On the other hand, it's really fast, no doubt about that. And we don't have any overhead at runtime, because at runtime it's already compiled, where the JIT has to go through this thing that we saw, interpretation C1, C2, and so on. Okay. Okay, and the small memory footprint, of course. Java, the JVM is bigger than that. That means we have some disadvantages. The JIT needs more time to start up, CPU overhead and memory overhead compared to AOT. Okay, let's take a look at a different approach then. And it's called CRIO. So I don't know if you know that, maybe some people sometimes know CRIO because it's a Linux project. It's called Checkpoint Restore in User Space. And it's in the kernel since 2013, so now for nearly 10 years. It's not really a new thing. And it was made to freeze or run a running container or application, which is interesting. I mean, we talk about 2013, and they already thought about this idea. And they could checkpoint this application or container, the state, to the disk and then restore it in the future somewhere. And that's the idea. And it's used already by OpenVZ, by Linux containers, Docker and Podman. They can use it. It's not used per se, but they can make use of CRIO. Right? So you can checkpoint a Docker container with, and also if you use Podman, it's the same. And they all use CRIO. I said this is a Linux project. I will come to that later. This is not on Windows, not on Mac, right? But by the way, who's running some production stuff on Windows? Somewhere? No? Ah, I had that. Yeah, some people do. Yeah, which is fine. But then, sorry, you can't use it. And on Mac, usually nobody uses that. But yeah, that's a fact. So it's only for Linux. It heavily relies on the proc file system. And you have to keep in mind that even on Linux, not all Linux distributions use proc. If you don't have proc, you can't use CRIO. Right? This is also a fact. Also, the reason why it doesn't run on Mac. Mac is some kind of Linux derivative, so Darwin is similar, but it doesn't use proc, so you can't use it. It can checkpoints all these things. I don't read through it. It takes too long. You can read it. It's a lot of stuff. Yeah, it's great. It's cool. Perfect. Yeah. Okay, we got that. So we have some challenges when using CRIO. If you think about, I create the checkpoint on this machine, and now I would like to restore it on that machine. Should be possible, right? If you have open files on this machine that are not available on that one, then probably not. Same for shared memory and stuff. So, it could be tricky. The same is true if I say, oh, I would like to run it multiple times on my machine. I mean, I can restore once, I can restore twice. No, you can't. Because it's bound to the PIT, which is on Linux the unique process ID. And this is only once per process. And if you now guess, what happens if this PIT is already taken by some other process? Yes, you're right. You can't restore. That's true. I mean, for CRIO, not for CRaC, but for CRIO, this is true. These are the things with the standard stuff. And now if we talk about the JVM, then you would think, the JVM is just an application running on Linux, so I could checkpoint it. Yes, you can. The JVM, no problem. The problem is your application in the JVM, because this application is the thing that has files open, sockets open to a database connection, something like that. It's not the JVM, it's your app, right? If we checkpoint the JVM, then we just close it. We say, okay, make the checkpoint, store the state, close the application, that's it. The next time you do the restore, you open it, the JVM will start, your application will start, and then it says, where's my file? Oh, where's the database? I had a connection before, now it's gone, and it will crash. And that leads me to CRaC, because this is the coordinated restore checkpoint. We try to coordinate the checkpoint from the JVM to your application. So the application needs to know when it is checkpointed and also needs to know when it was restored, because then you as a developer have the ability to do something, right? To close resources and reopen them, right? This is the idea, which is, it's mainly open files and socket connections. This is the problems. That means you have a database connection, you close the application because there's a checkpoint, then you need to close the database connection, and before it starts running again, you have to re-establish this connection again. This is the idea. Okay, so CReO, what we do is we bundle CReO with the JDK. We contributed code to CReO to make it work with the JVM because we need some hooks there. So we bundle it with the JDK to make sure that it's the right version. And if you have your doubts that, oh, I have a multi-threaded application, how can you make sure it shuts down everything? Well, we use JVM save points. It's the same that is used for garbage collection stuff. And I think you never really stop your threads just because there's a garbage collection going on. The JVM can do that, right? So, and that's what we use. We use the same thing. It comes with a pretty simple API. We will come to that. It can create checkpoints either using code or using JCommand. Who knows JCommand? Yeah, just a few people know that. It's interesting. Yeah, and it throws checkpoint exceptions in case something went wrong when creating the checkpoint. So we added 2 parameters. So when you would like to start your application, usually you have a fat jar or something. You started with the -jar stuff. So if you add -XX:, CRaC checkpoint 2 equals path. And the path is in principle the folder or the location where the JVM should store the checkpoint. So its state, right? So we have to let the JVM know, okay, if there's a checkpoint, what should I do? Where should I store the files? This is the folder. And if you restore, we just have -XX:, CRaC restore from, and we just point it to that same folder, and then it knows, oh, okay, if there's a checkpoint, I just load it back to memory. That's the idea. Okay, so we have these 2 new commands. It's an OpenJDK project, so we came up with the idea, and it's led by Anton Kozlov, which is one of our engineers. And we had the idea to do that, and then we thought this is so useful. It would be great if it would be a part of the OpenJDK. So we proposed that as a project. It was accepted. Doesn't mean it will ever make it into OpenJDK. So we are working on a JEP, but it might happen that, for example, Oracle says, well, it's not really cross-platform because it doesn't work on Windows and Mac, so it won't make it into Java or into the OpenJDK. So this is the drawback, but yeah, that's the current state. We will come up with a version of Zulu, which is our own JVM, next month, and that will support CRaC, so on Linux. And we also have a solution for Windows and Mac to give you an idea. I will come to that. So the CRaC API, pretty simple. It's just one interface called resource, has 2 methods, before checkpoint, after restore. That's the idea. I don't read through this. Because it's recorded, you can read that afterwards. It's just the stuff that I told you anyway. So it's, like I said, it's made, we have to make sure that you have the chance to close the resources and reopen them again. That's the main idea, right? So we have to find a way to do that. And how we do it is, you have, for example, a database manager, the stuff that the class that is in charge of connecting to the database and having this connection. And what you do is you implement this resource interface into this database manager, right? And then somehow you have to let the JVM know that this class is a resource, because the JVM doesn't know on its own. So we have to register this class in a context. And the context you can get by a class called core get global context. It's a static method. So that means you can get the context, you can register your resource, and then the JVM knows if there's a checkpoint, I call this resource. And then in the resource, it will call before checkpoint. Okay, so that's how it usually works. You implement the interface, you get the context, you register your resource into this context. And then the JVM will call it. There's only one context in the JVM, and you can imagine you have not only one resource, you can have multiple. Depends, right? And with this context, it maintains this list of all the resources, and it takes care about the order of the resources, because that could be important. If you have, for example, resources that depend on each other, that means the first thing you do when you start your application, you initialize the database connection because you need that. Then the next thing you have a next class, you need the database connection, and then you open a file. So that means the second resource depends on the first one. and it will only work if the first one is initialized, right? So that means you have to make sure that this order of resources is always in order. And what we do, usually what you do, you initialize them in the way you initialize the classes, right? You usually have something in the constructor and the factory method where you initialize the database connection and then the second resource. If you register them, these resources, in the same order in the context, then the context will make sure that they will be always closed and reopened in the same order as you initialized them. So that's the idea. After restore, we don't go into the details. It's too much. From the command line, if you would like to create the checkpoint, because that's the question how you do that, you have your running application. You call jcommand either with the jar file name or with the PID of the running program, and then you call jdk.checkpoint, and this will trigger CReU in the background to create the checkpoint in the JVM. That's the idea. And we won't do that because it takes too long to show all this stuff. But in principle, because who's using Spring Boot here? Great. Who's using Quarkus? I know that. Yeah. Who's using Micronaut, for example? Nobody? Oh, a few. So, in ideal case, you don't have to do that because these frameworks will do that for you. So Micronaut, for example, they do that. You don't even have to implement the interface, right? So because they know these are the resources, they will close it for you, they will reopen it, all these kind of things. You don't have to do that. This is only if you run your own app and you would like to create a snapshot and you don't use any framework, then you need to know these kind of things. And they are documented. So you can also create a checkpoint from the code. The question sometimes is why do I want to do that from code? Checkpointing means you close the JVM after the checkpoint. The reason for that is I talked about these trading applications. These guys have specific code to warm up the JVM. That means they exactly know when it's warmed up. So that means they can just at the end create a checkpoint. And they can make this dependent on if there is a checkpoint in that folder, then don't do it. If the folder is empty, then create the checkpoint. So that means they can do that automatically. And this is the reason why we have that also in code. Sometimes it makes sense. For me, I never use that, but there are reasons why you can do that. So the thing is, we just created this feature. We have no idea how you will use it. So we are a little bit dependent on the community, on the feedback, because we have no idea how you guys will use that. But that's the reason why we implemented everything that came to our mind. So the typical thing is, the reason is now, the question better to say, when do you create a checkpoint? If you don't have this specific code, how do you know when is a good time to create the checkpoint? So what you do, you run your application with a typical workload. Could be the test that you write. I hope you write tests. So if you do, then you can just run the tests. And you will see if you start the application with -XX plus print compilation, who knows that flag? Or you should know that. That's quite helpful sometimes. It prints out all the compilations that are going on. Really all of them, which is a lot. C1, C2, you will be surprised. If you start your application with that and you take a look at the console, it goes like, but at some point it will get slower and slower and slower because everything's compiled. And then you know this is now a good time to create the checkpoint. That's how we did it when we test stuff. We are working on a metric that the JVM figures out on its own because the JVM knows what it's doing, right? It knows how much code did I compile and how many compiles per second did I do. So we are thinking about a flag that you can ask the JVM, is it time for a checkpoint? And it says true or false. So then you know. And but this is not in yet, but we are working on that. Yeah, you observe the moment when the compilations are ramped down, and then you create the checkpoint, which is for testing stuff. That's fine. If you have a huge application, it might be boring to look at the screen with all the compilations. But at some point, like I said, it slows down. So the typical use case for CRaC, usually you run your app in a Docker container or in some container, and what you do is you create the checkpoint in the Docker container. That's easy. Now we have two different possibilities. The first one is you commit the state of the checkpointed container into a new image. right? For this, you have to need a second shell from the outside. The container still needs to be running. Then you create the state, or save the state in a new image, and then you have the image with the checkpointed files in the container. That's one thing, but this is not the best thing. So usually what you should do is you store the checkpoint not in the container, but somewhere on a volume, in a cluster, or on your machine, on your local machine. You can also do that. And then because we can point the JVM to the folder, you can point it to your local machine. So right, that means if you start it up multiple times the same service, it can all load from one checkpoint. That's the advantage. And the images are still small because we don't have to store the checkpoint in the image, right, in the container. But then, yeah, if you have it in the container, you can start it from there. So this is just a different way of doing it. And it depends on what you are checkpointing. If your huge application means what it is it's more or less a heap dump. If you have a heap of 100 gigabytes, you can imagine that the checkpoint will be around 100 gigabytes. If it's compacted, it might be slower, less, not slower, less than 100 gigabytes. But it's more or less a heap dump. So we compact the heap like with a garbage collection, but in principle, the state of the JVM is the heap, more or less. So we store that. And an interesting point is that because Creo is bound to the pit, it creates the checkpoint with everything that is bound to the pit, even off heap memory. So even if you use off heap memory, it will be checkpointed because it's bound to the pit, which is sometimes not everybody uses off heap memory, but some people do, and then it's really useful that you can even restore from off heap memory. Okay. So I already mentioned it's Linux x64 only. So we are working also on an ARM port, so it will come. But at the moment it's only Linux x64. So what about Windows and Mac? Because there is no JVM for Windows and Mac that has CRaC support. That means if you try to use the API, it will break in the IDE and will say, I don't know the package, I don't know the class, so what's going on? So we have a solution for that, and you will find it here. github.com CRaC org.crack. This is a library, and it's also on Maven Central. You can implement it with Gradle or with Maven like this. And what we do is we have some kind of a shadow of the API. So you code against that library. The library will figure out if the JVM supports CRaC or not. If it supports CRaC, it will make use of it. If not, it will do nothing. So with this, you can code on Windows and Mac, and you can then deploy it to your Linux system, and then it will work on the Linux system. And you can just, in the IDE, it won't break. That's the main idea. And that's what we hope will satisfy Oracle in terms of it's not cross-platform, right? Because the CRaC functionality is not cross-platform, but it won't break on Windows and Mac. So a few words about compatibility. This is not really, it is true, but it's not really bound to the Core I and Core 9 stuff. It's more the CPU level. We name that upgrade. So that means if you create a checkpoint on a Core i7, for example, CPU from Intel, then you can restore it on a Core i9 because they are backwards compatible. Because the JVM is quite smart. It knows about specific things that can be optimized on a specific processor. And what's not possible at the moment is downgrade. So you can't really create a snapshot or checkpoint on a Core i9 CPU and then restore it on a Core i7 because the code, the JVM code from the Core i9 will use optimizations that are specific for this processor type. And they are not available on this Core i7. Why I tell you that is if you do something like cloud deployments, then, for example, in Azure, you can define so-called node groups. And one node group, you can define the CPU architecture. And then it's guaranteed that it is, for example, Core i7, whatever, for all the nodes in this node group. That's good. If you run a Kubernetes cluster, it can run multiple node groups in the same cluster. And that's the problem, because then it can mean you have one node group with ARM processors and the other one with Intel. That won't work, right? So this, if you use that in a cloud environment, you have to make sure that all the nodes running on the same CPU architecture. Otherwise, you will run into trouble. That's something you have to keep in mind. apart from that, all virtualized Linux environments, it will work on all of them. If you run it, for example, in Parallels on Mac or what is the other one? I don't know. All these VMware on Windows, for example, as long as it's x64, it will work. So I can create a snapshot on my Linux machine on an Intel and can run it on my, not on this one, but on my other Mac, which is an Intel one, and it will work in Docker. Okay. Demo. Yeah, so I created a new demo, which is a name service, and it's 258,000 names. I found them on a database on the web. They are in a JSON file, and it's just boys and girls names. The service is, give me 5 random boy names, right? First names, or girl names, whatever. That's the idea. And the code is pretty simple. The main method, this is the plain Java stuff. This is not using any framework. So if we call the constructor, it will register this resource to the context, right? And then it will call the initialize method, and this one will load all the names from the JSON file. First time I have to load it, and then it's not if it's practical. I would never do that this way, but to give you an idea. And then after that, I just print random girl names and 5 random boy names. That's the main thing. And then I print out the time it took to do that. So this is the idea. Okay. Then I have this after restore. That means if I do a checkpoint and the next time I restore from the checkpoint, this method will be called, not the constructor or something, right? Because it's like a snapshot. The code was already running, I just snapshotted it. So there's no need to go to the initialization again. In this case, I just can directly print out the names because I loaded these files already into my map or wherever I loaded them, right? So it's no need to do that. You can already here, you can imagine that it's faster. If I run that side by side, this one, I put them in a Docker container, I run the stuff. You already see I need privileged, which sometimes is a problem. The problem is that Trio needs that. There is a new version of Trio coming, which is called rootless, and then we don't need this anymore. But at the moment for Docker, we need privileged access, which is this is a little bit of a drawback because it gives you more rights in the container that you usually need. But for this one, we need only for creating the checkpoint. For restoring, we don't need, but for creating it, we need the privileged thing. So here I just start the jar file, and on this one, I just run it here with the pointed to this folder, right? So that means I call Java and restore from that because I have a checkpoint in that container. So what happens is, that was too fast. Here, I also put out JVM startup time. This is JVM startup time, 20 milliseconds. That's what people say JVM is so slow. Because you can measure that with an MX bean. This is really the startup time of the plain JVM. It's just fast. And then loading the files took 1.3 seconds in this case. And then it spits out the 5 names for girls and boys, right? The whole time was 1.3 seconds. When I use it from the checkpoint, I don't have to load all the files, right? So then, because it's already there, then it was just 48 milliseconds. Of course, this is only for the first start. Second time I call the service, it's in memory, it will be the same as that one, right? That means this is just an example, but we have, for example, companies like Brawl Stars, you know that game maybe from Supercell. It's, if you have kids in the age of 10, boys probably, these people know about Brawl Stars, and they have this problem that if they have to scale up, then they have to start up the Brawl Stars instance, and that takes some time to start it up. They could really benefit from stuff like this because they could have a warmed up instance and then it would be there like this in milliseconds because they don't have to go through all the startup thing, right? So this is for one example where it makes sense to have the speed at the first time you call it. Right? It's not for every service because for name service, I don't mind if it's the first time takes 1 second, second time 50 milliseconds. As a user, I don't care. But for people like game companies, you will feel it. If the game stuck for 1.5 seconds and you say, oh, what's going on? Oh, shit, I'm dead. Right? Something like that. So it could be useful. This demo is available on my own GitHub repo. There's another one. This is the plain Java code. I also created a Micronaut demo, which has the same thing in there. It's just here under CRaC. So that's cool. I showed you a demo that I didn't really show. The question is, how good is it really, right? Of course, we didn't only do our own playground stuff. We tested it with Spring Boot, with Micronaut, with Quarkus. I have to say, these demos have been made with hacked versions of Spring Boot, Micronaut, and Quarkus, because at that time, that have been created in the beginning of last year, there was no support. So that's you can find the stuff on a GitHub repository, but you will see that, for example, for Spring Boot, we hacked Tomcat, and then we told Spring Boot to use this Tomcat to make it work. But I had a call with Spring 2 days ago, and they told me they are working on a solution and they hope to get CRaC support as a first-class citizen in June this year, in their next version. I think it's 6.1, something like that. So we hope it will be in there. Micronaut has perfect support for it. Quarkus, it's a little bit disappointing. They say they have support, but just try to find it on their website. There's nothing in the documentation, so I have no idea. The only thing that I have working is our own version, which is, and you pointed to our repository. So that's where you say it supports CRaC. Yeah, this is the stuff that we did, but they said they support CRaC, but I couldn't find anything on their website yet. So, but we are in contact with them. This have been the times after using CRaC. So Spring Boot took around 4 seconds, and then it was 38 milliseconds to start it up. And then Micronaut, it was 1 second, which is fast, right? But 46, Quarkus was 980, 33, and this is just an XML transform. The interesting part here is, no matter how long these bars are, in the end, they are more or less the same. The reason is we just load stuff from the disk. It's all dependent on I/O only. There's nothing else, right? Because this only takes that long, especially Spring Boot. It does a lot of stuff when it starts up, loads lots of things, and it just takes a long time. And it also takes a long time to optimize all these things and compile it. This is all done when we create the checkpoint, and then we just load it back to memory, and of course it's fast then. And this is true for all these things. Summary. CRaC is a way to pause and restore JVM-based application. It doesn't really require a closed world. Like with a native image, a little bit of a drawback is that GraalVM needs to know all classes at compile time. So in the JVM, we are not used to that. So it doesn't matter. You can even load a library at runtime, and the JVM will just say, yeah, okay, give it to me. I will compile it. That's fine. You can't do that with GraalVM. You have to always tell GraalVM, okay, these are the classes that will be used, and then it needs to compile it. Okay. It will start very fast with full performance. And the good thing is with CRaC that you are in charge of defining when to create the checkpoint. That means if you say, oh, I'm just interested in having the JVM startup fixed, you do it in the main class. If you say, oh, I need to warm up my code, whenever you like, you can create the checkpoint and restore from there. Yeah, there is no hotspot identification or method compiles needed, because if you wait long enough, then you create the checkpoint, then everything's done. So you don't have to go to the de-optimization phase and all that anymore. We have improved throughput. It's an OpenJDK project, and it can also save some money, because we saw that in the numbers of that Belgrung test, that the startup, it was memory, but it was huge with the JVM. It was a gigabyte, something like that. The reason for that is that this thing is the JVM startup time, and we saw that this interpretation, compilation, that has to be done in the beginning. This is CPU utilization, that's time. And you probably know that. And in the beginning you see this peak, and then it drops, because here all the compilation is done, and then you don't need that many CPU utilization to run your code. But you pay for that, right? So that means if you have, for example, some 64 core CPU, just to make it as fast as possible, then you pay for that, but you only need maybe 32 cores. That means if you create the checkpoint here once, and then start from there, you don't need 64 cores to run your application. You just need 32, and that can save a lot of money, right? So you just have to think about these kind of things. So that means we can eliminate startup time and CPU overhead over time, definitely with that. We can't really do something against the JVM memory footprint. This is bigger, it's a JVM. But like I said, if you have applications where you handle a lot of data, then usually the data that you load into memory is much more than the memory footprint of the JVM. So it's an argument, but it depends. So it doesn't mean GraalVM is a bad thing. So don't get me wrong. If you have small microservices that don't need a lot of resources, then GraalVM is great to do that. Because it's really small, it starts fast, that's perfect. But apart from that, as soon as it gets a little bit bigger and more complex, then I have my doubts that it's really that much better. Everything that I showed you is on github.com/CRaC. There you will find an OpenJDK build that we provide that has CRaC inside. It's a 17.02 version as far as I know. You will find all the demos there. You can try them on your own if you like. You can also see how we did that. So because I saw at DevOps France there was a guy who did a CRaC talk, and he used one of my demos, and I was like, oh, that's cool. And he used just the code the hack Tomcat that we used for Spring Boot to do his demos. With that, I'm done. I mean, I'm not sure how much time we have. I think not really a lot, right? Because I also have the demo. I can show you live if you would like to see it, but I think it's clear, but we can do that anyway. One thing I have in the end, because Gerrit asked me for that, if you use Azure Platform Core and you could do a review on this link, Gerrit, which is one of my colleagues, we run also Fuji.io, he would be very happy if you can do that. So if not, it's also fine, but if you, then that would be awesome. Now let me show you my little demo. Should work, let me see. So the first thing that I do is, let me close IntelliJ. That's the Micronaut stuff now. This is running on my own server at home. Yeah, it's presentation mode. Wait. Where's the screen? On the left or on the right? Ah, there it is. Okay. Okay, that's my browser. Oh, okay, one. There's one share. Can you read it, or is it too small? You have to come closer to read it. Okay, so here we go. So the left thing, oh, now I have to look there, is, I'm there, okay, it's, I run the Micronaut application just directly from Gradle. Okay, there we go. And now what I do is, it's on the right side. This is this name service. And I'm calling the service as I have a gender male 10 names. Okay, that's the thing. And let's see if it works. Okay, here we have the 10 boy names, and it took 2.1 seconds on my machine. This is including loading the file, right? It's a lazy service. That means the first time you call it, it will load the files in memory and then will give you the result. If I call it again, you should see different names and it will be fast. 19 milliseconds, different names, right? Because now everything is in memory. That's clear. Okay, that's the first thing. And now we do the same stuff, but we use a Docker image. And so what I did, let me show you. Because Micronaut has this functionality already inbuilt. So you create your app, this is this thing, and then just have a Gradle command. It's also for Maven, you can do that. It just says docker build CRaC, and that's it. It will create a Docker image for you, including the checkpoint. And to warm up your service, they provide you the ability to have something like a custom warm-up script. So what I did, I just did a curl on my own endpoint so that it was loaded once. And then now I run this one, right, which is easier. Just put it in the, oh, here's my, yeah, it's there. Okay, so we start that. And it will tell us that this is it was restored. Okay, so we go again to this one. This time we do girls. Female. And now 15 milliseconds. First call. Because it just got directly, it's the warmed up service, right? So we don't have to warm it up. So you get an idea of what you can do with that. So it's always in the range of, depends, like 15 to 100 milliseconds, depending on how many resources you have to reopen. But you can really get the same startup speed as a native image, but you can keep the JVM, which is a big advantage if you're a Java developer, because you don't have to leave the Java environment and all that. And with that, I'm done. So if you have any questions, just...
Any questions? Yes.
Oh yeah, so depending on my changes as a developer, I have to create another checkpoint again, right?
No, you don't have to.
No?
Because the checkpoint you only need for production, right? It's just a checkpoint.
But before deploying to production,
Yes, if you do the deployment, then you create the checkpoint. If you use, for example, the Micronaut in this case, it will create it anyway for you. You just create the Docker image. It's one call. You just do Gradle / and then Docker CRaC image or something.
With the warmup script, I can put it in my CI/CD.
Yeah, you can do that in CI/CD with this. It's pretty simple. But I agree. This is people sometimes get that wrong. You don't have to do any changes that if you do during the development phase, because then you don't need the checkpoint, right? It's just in the CI/CD. If you go to release or production deploy, then you need to create the checkpoint, because then it's, and this is they save it in the container, but like I said, I would prefer to just store the checkpoint maybe locally on your cluster and deploy it to somewhere in your cloud environment on a volume, and then just point every container to that volume and then load it from there, and then it's pretty simple. And then
what happened if we would try to restore in your version of the application with no checkpoint? Is there some kind of security built in that they?
If you have, if you would like to restore, and there is no checkpoint.
No, if I would like to restore, I have a checkpoint, but of an older version of an application.
Oh, this will
change the code. So
you just have the follow. Yeah,
pipeline.
yeah, it will crash.
It will crash. Okay.
Yeah, it will crash. Definitely, yeah.
So the checkpoint, it creates a checkpoint of the JVM plus the application. So if you have an application with huge in memory, let's say 32 gig, so how does the boot up time work? I mean, the restore time work?
The restore is, so you have to think about that. For this application, the checkpoint is around 30 megabytes. It's not one file, it's a couple of files. There's one bigger one and then a lot of small ones. If you have, for example, 100 gigabyte in memory, then the files will be 100 gigabyte. We did some tests with a 128 gig heap, and the startup time was still around 70 milliseconds. If you load that from an SSD, it's really fast. It's not really that slow. I was also, it will be slower. Yes, of course it's slower than 30 megabytes, of course. But still, it's much faster than starting the JVM and do all the compilations. This is always in the range of seconds, and this is always in the range of milliseconds.
Even 128 gig
Yeah.
is less than a second.
Yeah, I mean that if you put it on a normal hard drive, of course that will take longer. It really depends only on I/O. If you have slow I/O, then it will take longer. If you have fast I/O, then it will be fast. Right? You can even think about putting it in a cache, the checkpoint. Right? Use Redis, put it in a cache. Then it's even faster. So you can do a lot of things with this because it's just files. Wherever you put them, if you have access to them, you can load it from there. So that's the speed is there's no difference from starting up CRaC and starting up a native image. It's more or less the same. More or less. Native image could be faster, maybe, but then we talk about 20 milliseconds compared to 50 milliseconds, which is still fast. Yeah.
Is it an enterprise one you think?
If you have JVM Enterprise, then you get also the same speed. But all the frameworks that use GRA, like Micronaut and Quarkus and Spring Boot native, they all use the Community Edition.
CRaC.
No, this is free available for production also. If it will be in Zulu next month, it's freely available also so we don't charge for that, because we just do the implementation of the OpenJDK project. So, and we hope others will do the same. So maybe Tamarin will pick it up and others and use that because it's just useful. Yeah.
Apart from aspects of architecture, if you have an application that has two phases,
Mhm.
works in one phase, does a certain amount of things, runs a certain amount of methods, and then has another phase which is run at another time. You would have to take 2 checkpoints, one at phase 1, one at phase 2, and mix those together, right? To have like the proper startup time.
You should have one checkpoint after the second run, because that includes the first.
But
Except you need this first step because it does something for you, but usually it's really just, it's like a snapshot. And if you say it does it first this thing, and then in the second step it does the other thing, if there's no need to wait for the first one, then you can create the checkpoint after the second, and then it includes the first one, right? It's everything in there. Everything to that time is in the checkpoint.
the JVM doesn't forget about all the optimization, all the loading.
No. It's because it's the state of the JVM, right? So and if it runs for a day, it did all these optimizations, and the state is fully optimized, and this is the state you restore, including everything that was done before. Yeah, that's the idea.
Is it possible to exclude some data from checkpointing, because sometimes some of the data can be dynamic? In this case, like if you load data from VCS, okay, this could be dynamic, right? And database will change.
Yeah, that's a good question. So what I recommend is, if you have stuff like that, so you don't have to checkpoint everything, right? So not every service needs to be checkpointed. Only if you benefit from startup. Usually that's microservices that you have to scale out. Then you need fast startup time. It can be a Cassandra instance, for example, that you have to restart every day, which can take minutes. You can benefit from that because it will start faster. If you have sensible data, or data that's, for example, time dependent, you shouldn't create a checkpoint. Or you have to make sure that you first unload the data and then reload it after the checkpoint. Because the problem is, if I talk about time, if I create a checkpoint now, that means I freeze the state of the JVM. That means also I freeze the time in the JVM, right? When I restore tomorrow, the JVM thinks, oh, it's today. Because the JVM doesn't know. If you have time-dependent data in your caches, for example, then you have to update them to the date you restore it. Otherwise, you will handle suddenly old data. All these things, you have to think about stuff before you can't just blindly create a checkpoint and assume everything will work fine. So especially if you have time-dependent data, or if you have data where you say, I load that from an S3 bucket and I keep it in memory, but I don't want to have that in the checkpoint, then clear the data before you create the checkpoint and load it after you do the restore. Of course, it will take some time to load the data back, but this is how I would do it, yeah. Yes?
Won't the JVM synchronize with system time?
The JVM itself, yes, but the data in the JVM not. But what we do is when we restore, we set timers in the JVM so that you can just synchronize to that timers your data, so that you can make sure that everything's up to date again.
Another question, is there any protection against manipulation? So is it possible to inject bytecode into the snapshot?
No,
and
this is binary data. So
Okay.
because it's the heap, it's really the stuff that is in the memory. It's no bytecode anymore. This is really binary data that's in the memory that the JVM handles, and this is stored. So you can check the files, you won't find any text in there. It's really just hex data where you can
with some
probably
effort
you could hack it somehow if you have enough checkpoints to figure out, but I mean the question is really how can you access the checkpoint, right? Because this is a file that is somewhere on your infrastructure. If you can make that secure, then there is no reason. And even heap dumps, just take a heap dump and tell me what is in the heap. So what was the code? Okay, no chance. It's no, usually not. But there's not, if the question is if there's any specific security specifically to that, no. There's nothing apart from that is a heap dump, and that we just hope that nobody will really be able to restore stuff from the heap directly, which is, I mean, never heard about that.
It's just like a backup, just don't leave it open.
Yeah, well, I mean, yes, in principle, this is really like you store the current state completely on disk. That's what it is. Yeah, in binary format, in multiple files. So yeah, that's it.
Probably a dumb question, because you can solve it in other ways. There's no interpreter to understanding a CRaC checkpoint, right?
No.
I mean, you can do, of course, by spinning it up and then doing a dump and analyzing what.
I can tell you a little story if we have the time. We can also.
Yeah.
So I was last year. I gave a session about this in Baltimore, which is close to Washington, and there's all the CIA and FBI stuff. So and people from these institutes came to my session, and where you ask questions about, oh, how can I do this and how can I do that? The first thing that these guys said was, this is awesome. We can hack other systems by doing that. We can inject checkpoints into JVMs. I was like, what? So they, yeah, I think if you spend if you think in these dimensions, there are probably ways of hacking other systems by injecting checkpoints if you have access to that. Sure, that would work. Maybe, I don't know, because it's just to give you an idea what these people think. It's they also had the idea to remote control machines using checkpoints and these kind of stuff. It's really crazy.
I mean, if you have access to one system, can take a checkpoint, can analyze it, replace stuff.
Yeah, theoretically yes,
And
but
then
like I said,
take
it's
checkpoint again and then replace it.
there's no clear text in the heap, right? So this is not something where you can see, oh, this is a command or this is a loop or something. It's binary code that's in there. So you can't just change this bit and this byte and hope that it will have this effect.
Yeah, but if you're able to take the complete checkpoint
Yeah.
data and then fire that up again, analyze
Yes,
it,
yeah.
again,
Yeah, absolutely.
take another checkpoint,
Of course.
and then replace
Yeah,
your
yeah.
checkpoint, you're possibly able to manipulate the company
Yes.
to then fire up
Yeah.
tons of containers
Yeah,
that all are controlled by you,
absolutely. Yeah, that would be possible.
which would be pretty interesting to then take over like a complete AWS
Yeah.
system.
So there you go. Just
Just
call the guys.
That's how Bitcoin mining makes sense again, right?
Ah,
Got
interesting.
one other question, and then we'll take a
Yeah,
short
okay,
break,
sure.
because
And what triggered me was the opportunity or the cost efficiency in other environment,
Yeah.
especially when using Spring Boot, because we see that day by day. But as far as I understood, we have some problems with if we have some states for database connections and custom states and something like that.
It depends. So if it's just a database, the database is not affected, right? So because the database keeps running, you just
Just the application with joining.
yeah, the application, because we give you the chance to close the database connection at the checkpoint. Before checkpoint, you can close it, and after restore, you can reestablish.
Yeah.
And with this, it's no problem to do that.
Okay.
So that would work. Yeah, it can really save money. It depends on the use case. Not everybody has that problem. But if you, I know we have companies, they addressed us and said, you know what, we bought the biggest instances in AWS just to keep this peak in the beginning as low as possible. And then they pay a lot for that. And it's maybe for 2 minutes or for 4 minutes. And then after that, it drops down to 50% of that, but they can't get rid of that. With this, you can, right? So the other thing is to come back to GraalVM stuff, which is nice. It's fast. We saw that. Not that fast as the JVM. It doesn't help you with warm-up stuff. With this service that I showed you, GraalVM wouldn't be a benefit because it's a lazy service. First time I call it, it has to load this stuff from the file. It's the same time. It starts up fast, yeah, great. But then warming up the application, it won't help you there. And with CRaC, you can, because it's up to you, you can decide where you create the checkpoint. It can help you also with warm-up, so that's a differentiation there. But now I think
Thinking about, I don't know, for deployment sequence, and letting the new pods start up, run the applications, and warm them up. I don't mind.
mhm.
Let's take that time. But then after some time, I don't know, minutes or
Mhm.
I don't know, after an hour, I'm taking a checkpoint, I'm creating a checkpoint, and then just restart the applications as they are, but with more freedom towards the CPU limits.
Yeah, exactly. You start from there where you left the machine.
Yeah.
exactly in that state, and it also uses exactly the amount of CPU that it used that time. That means the peak is gone. It was in the beginning, yeah, and that's the big benefit. It starts up fast. Yeah, exactly. Yeah, yeah. That's one of the benefits. Yeah. But now I think it's time for.
Yeah, because.
Yeah. Marcus is already
Marcus is
sleeping.
no, not sleeping. He's thinking when
Yeah.
it's